honors chemistry students, so you should have already watched that introductory video on nuclear chemistry. Hopefully you learned a lot in that. I am going to break things down a little bit more for you right now in this video. So our subatomic particles, you already know your subatomic particles. You know that protons have a positive charge, neutrons have a neutral charge, and they're both located in the nucleus. And that electrons have a negative charge and they're located outside of the nucleus. So, radiation. You learned in the video that nuclear radiation is an emission of energy resulting from the decay of atoms. It comes from the nucleus. It's nuclear radiation. It comes from the nucleus. And basically what's happening is an unstable nucleus is emitting a particle or energy. So it's emitting energy just like the definition says. And that energy that's reduced is either an alpha particle, a beta particle, or a gamma particle. So there's alpha, beta, and gamma radiation. Okay? I'm going to talk about each one of those. So an alpha particle is the same as a helium atom. It's the same as a helium type of thing. It has 2 protons, 2 neutrons. We know that helium is He2 and with a mass of 4. So we know that there's 2 protons and 2 neutrons, okay? A alpha particle will always look like this, 4, 2, He, or just alpha with a 4 at the top and a 2 at the bottom. Okay, that's always an alpha particle. A beta particle is an electron. So think of an alpha particle as a proton, a beta particle as an electron. So we have electrons. We know that electrons don't have any mass, so it has a mass of 0, but we do know it has a -1 charge. Okay, so you can write a beta particle like this, E0 -1, or just a beta, which is the same as this. And then gamma radiation is just straight pure radiation that comes directly from the nucleus. It's just phrased as Y, and it has both a 0 charge and 0 mass. So radiation, alpha particles are the weakest, beta particles are in the middle, and gamma radiation is very strong radiation. So balancing nuclear equations is what we are going to do with this nuclear chemistry. So you know what nuclear chemistry is, you know what beta, alpha, and gamma radiation is, so we're going to apply that to some balancing equations. So we always know that we can't create or destroy mass, so our atomic numbers must always balance and our mass numbers must balance as well. So we can see here in this example we have uranium. Uranium has an atomic number of 92 and an atomic mass of 238. It's telling us that uranium is going through alpha decay. We know that alpha decay is represented by this 4/2 He because that is an alpha particle, okay? So, since we have 4 at the top and 2 on the bottom, that means that we need to subtract it from our original atomic mass of 238. 238 minus 4 is of course going to be 234. And then 90 plus 2 is going to be equal to 92. So we have this new particle that we've created. So if uranium goes through nuclear radiation, we're going to result in this molecule with a molecule of an alpha particle. We're going to do more examples of this in a little bit. Sorry, Mr. Lewis entered, so I had to pause for a moment. Beta decay is our next thing we are going to look at. So beta decay, if we start with this TH molecule, let me actually look up what element that is because I am not positive off the top of my head. The element TH is called thorium. Okay, learned something new. So if we start with thorium, so in here we just started with uranium and broke it down into thorium and a helium. We're going to now start with thorium 234 and 90, what we have right here. And we're going to break it down further using beta decay. Okay, we know that beta decay is a beta particle is an electron or E0 -1. So if we have a -1, we need to, we need to include a 91 here. Okay, we need to include a 91 for our atomic number because we're adding an electron, so we're changing our atomic number. This is the only time that we can change our atomic number. But notice the atomic mass isn't changing because we're not changing anything about the mass. So we're starting with thorium, getting rid of a beta particle, and then creating protactinium. Sorry, I'm not very good at saying that one. Gamma radiation is very simple. There's no change in atomic mass or an atomic number. We're starting with boron 5 with atomic mass of 11. We're breaking it down to boron 5 with atomic mass of 11 and just emitting a gamma radiation. Nothing is changing about the mass or the atomic number. So let's do an example here. Hopefully my screen is the same way that it should be. Oh goodness, I really hope I didn't screw this up. Oh, nuts. Okay, well, my screen is backwards, so let me pull up. Let me think how I'm gonna do this. I'm gonna stop this video for now, and then we're gonna start a new video going over examples. Okay, thanks.